This is a fairly short video to introduce you to time series modeling. It does not replace the chapter from the book. There's a lot more detail in the book, and if you look at any of these topics, you'll find there's an immense literature out there, and it gets mathematical quite quickly. But most of the kind of time series data that you're likely to encounter, you can handle fairly easily in Excel, and At Risk does give you a very quick capability of doing some simulation modeling with time series. So all I'm going to do here is really cover the mechanics, so that sort of a quick start of how do you use At Risk to do a simulation model for time series data. The important conceptual thing for time series data is to think of a time series as you're trying to predict or forecast some level, really at some time t, and it's going to be equal to some sort of average level that you predict from the data you've got, plus possibly some trend if it's trending over time, plus some seasonality, plus some random component, which is sometimes referred to as error. So when you see error, think of the random fluctuation. So any time series you look at, you can think of that if you look in the past, there's kind of an average level it's been at. There may be some trend either up or down. There could be some seasonal patterns, some regular variability. And even if you have all of these three things and have kind of modeled them, there's going to be random fluctuations that are accounted for by various other things that you don't have data on. So there's some random fluctuation around there. And the whole idea of time series modeling, I'll use the term short-term forecasting, is to try to model these three things, level, trend, and seasonality, and then approximate or simulate the random fluctuation around those three things. And the important thing is to take into account the trend and the seasonality that exist. Otherwise, these time series methods will basically view all of the fluctuation as random, when in fact some of it, in fact a large part, may be modeled as trend and seasonality or sort of predictable patterns. So some of it is predictable and some of it is not, and that's what we want to separate out. And you can find lots of references that'll show you formulas of how you can actually model the trend and seasonality and level in Excel. At Risk makes this fairly automated and for most cases relatively painless in order to do this for you automatically. And so that's what we're going to look at, is how At Risk can do that. So here I have a data set of monthly unemployment rates for the state of Alaska and for various regions within Alaska. There were a lot more regions, but I just kept it to a manageable few here. And it's monthly data from 1990 to fairly close to the present time. First, I'll show you how you handle a single time series, and then I'll show you how you can handle more than one of them at the same time. So if we just look at the statewide unemployment rate and highlight the whole series. So September 2019 was the last available data when I downloaded this. Even before going to At Risk, it's useful in Excel to put in a graph of this. And so when you look at this, one thing you'll notice is that, think in terms of level, so if I had to predict a level, you know, it's somewhere in the middle of this. But trend, there does seem to be some kind of trends that last for some period of time. I wouldn't call this a long-term trend, because what you can see is that it goes down and it goes up down, then up. As long as there's multiple switches, it's not a long-term trend, but there does seem to be, over the first period of time, a downward trend and a brief upward trend, downward. And right now we seem to be on a kind of fairly long-term downward trend, very slight. The other thing that's much more apparent is there is a seasonal variation, because there's a regular repeating pattern in this. Excel will actually let you see some of these things. If you highlight this series and right-click, you can add a trend line. And notice the linear trend is showing a long-term downward trend, but it leaves out an awful lot of the detail. It doesn't pick up the seasonal pattern. It doesn't pick up the fact that it hasn't always been down. There have been periods when it's been going up. If you click on a moving average, the moving average, a 2-period moving average, actually seems to model it pretty closely as you increase the number of periods. So a moving average just looks at the past X number of periods, 3 right now, and averages them, and that's your prediction for the next period. And as you increase the number of periods, notice the black lines are fluctuations are getting smaller. You're smoothing out this pattern. If you go to full year, you now have kind of approximated what that series looks like in terms of just trend. The seasonality has been removed. You no longer see it on the black line. What you see is a little rising period, then generally downward, another rise, downward, up. So you've eliminated the seasonality essentially with 12 moving periods. If you go longer, it will now start getting noisier again, because you're now kind of introducing the seasonal pattern back in by going more than 12 months. So Excel has some automated things. You can also put in other kinds of trend lines, but it's somewhat limited in what it will do. And what it won't do is it won't allow you to simulate the uncertainty. So the random component is not being handled at all by basic Excel functions. If you go under at risk to time series, to fit the time series, this is the dialog you get. There is this nice little button, auto detect, and we will use it. And I would tell you it generally works pretty well. Sometimes it doesn't. So you've got to use your eyes and your head a bit. You will want to do auto detect, but you also may want to manually override it. One thing I've observed is in some data sets, auto-detect does not correctly pick up the seasonality. It may not notice that there's seasonality. Sometimes it does, sometimes it doesn't. And the period for the seasonality, it often picks up the wrong period, and so you may want to override that. So if you have monthly data, it might find a seasonal period of 6 months, and if it's monthly, you really want it to be 12 months, so I would change it. The other thing you'll notice is the red warning that's here. Variance appears to be non-stationary. Sometimes it'll say mean appears to be non-stationary. Sometimes it'll say both. When it says that, that's a warning to you that it's not able to separate out the trend and the seasonality from the random component. Right now, if we were to ignore that and just go to fit, it has fit a number of different models. This is an autoregressive scheme, so it's detecting that there is correlation over time. Where it is at the current point of time depends on where it's been in the past. So it is modeling that part. But if you look at the forecast period that's showing here, the red is just one individual path. If you click this little button here, you will find that the red is going to jump around. Yeah, notice the red keeps fluctuating. It's showing possible simulation paths. If you were to run 10,000, you'll be running 10,000 of these red paths. But what's more relevant is to look at the black line. That is your actual mean forecast. And then some kind of confidence intervals, 50% interval and a 90% interval around that. But notice the black path, it's pretty much straight horizontal line. It's forecasting an exact level period. It's not picking up the seasonality at all. And in fact, it's not even picking up that the unemployment rate for the past, almost 10 years has been generally below that black level, because what it's doing is looking at this entire time series as if it's random variation, because we didn't pay attention to that warning signal about the variance not being stationary, and we basically didn't do auto detect, we didn't manually do anything. We basically just said, fit the time series models to this monthly unemployment rates as if they're all random variation. And that's what you'll get, is a fairly level forecast that is approximately somewhere in the middle of all of this data. So if we go back, and instead of doing nothing, let's try the auto detect. Auto detect, notice first order differencing. If you were to use stock market data like we've looked at, or we looked at Bitcoin prices, trying to model the Bitcoin prices over time is nearly impossible. It's way too much variability. But if you look at the week-to-week changes, it becomes more manageable. That's first order differencing. That is the most common thing that will be picked up. You can override this. You can do second order differencing. And it seems to actually make it a somewhat more regular pattern. But if you trust the auto detect, it's doing first order differencing. It is also done seasonality and additive seasonality. There's also a multiplicative, first order differencing and second order differencing for seasonality. But additive seasonality just says each of these periods, there's some plus or minus amount due to the seasonal fluctuation. It has correctly picked up a period of 12. If it had something else, I would probably override it here, since I know there's 12 months in a year. If it picks up something smaller, like 6 months, there's no harm in going to 12 months, because that should include any pattern that recurs within the 12-month period. If it picks up something longer than 12 months, you might want to keep it there. It might be actually picking up a, quote, seasonal pattern that is longer than just the time period in the data. So there might be a biannual effect every 24 months. I can't think of a good example where that would happen now, but it is possible if it picked up a longer period than the periodicity in the data, you might want to keep it. So generally I set this, if it doesn't pick up the right number of periods, I generally override it. If we go with that auto detect and we fit it, we get a number of models. The best fitting one, according to the AIC criterion, is an autoregressive moving average. Autoregressive part takes into account that there's a correlation over time. So where it's going depends on where it's been. And the moving average is picking up. Usually moving averages will try to accommodate for trend. And it's a little hard to see where the black line is here. But it does, you notice the shape, it is picking up the seasonal trend. If you actually go to the moving average, the second one, in some ways it looks a little bit better. It's a little less noisy. A noisier prediction is generally you'd like to avoid, but bear in mind the future is uncertain. So being more precise is not always a good thing unless it's more precisely correct. So the moving average gives you a narrower range of forecasts, but if it's in the wrong place, that's not an advantage, it's a disadvantage. These numbers seem to be pretty close, so I'm not sure that it's a much better fit for this one. So I might actually be inclined to go with the moving average here, since it seems to be a somewhat narrower range. And it looked pretty good. This does not look better to me, the third one down, so that one's narrower. So one thing you might do, generally, it's a good idea to consider alternatives. So let's take the best fitting one, and let's just do the last 3 months of 2019. So I highlight 3 cells, click OK. It puts in those forecasts. Notice the brackets around the formula. It's an array formula, so you can't change. If you wanted to add an output to this, you couldn't add it to this one cell because you'd be changing part of an array formula. So all 3 cells are sort of locked together. If you wanted to do if you wanted to set an at-risk output for the first one, I would create another column saying equal to that cell, and you could make it an output. All of this stuff is the type of model with its mathematical form. It's using seasonality, which it's adjusted for, and given it a name, and so we could do that forecast. One thing we might do here is just fit that again and see what the second one looks like. Do that fit again. Take the moving average. And there's the moving average forecast. We might want to compare these, so let's call this autoregressive moving average, equals C359. Copy them down. Add output. Actually, so you can get the naming to work a little better. So we'll do this as October, November, December. Now let's see if we can. And should work for the moving average too. Let's run this. So a couple things to look at here. Let's just compare the 2 December forecasts. So you notice they are slightly different. The mean forecast for unemployment looks to be about 0.1% higher, 6.6 versus 6.5, well, maybe 0.5% higher. Half, 1/20 of a percent, 6.56 versus 6.62%. Using the blue was the best fitting one. The red looked visually a little better to me. If you look at the 90% confidence interval, plus or minus 0.004 almost, and a little more than 004. So like my eye detected, the red is a little narrower forecast, which could be a good thing, but of course only if it's actually closer to the reality. So one thing, we're not in December yet, I guess we could look up, see what the October one is and see how that compares. So we might be able to find the October one. I'm not going to look for it now, but you'll notice that it actually let's look at October just by itself, overlaid. And again, the moving average on the blue seems to be, well, it seems to be a little bit lower. The confidence intervals are very close. It's actually slightly less variable. So I might think that the blue is, oh, actually, no, which one's slight? No, actually the best fitting one was a little less variable in October. Very little, it's almost the same width of the confidence interval. By December, start seeing a little bit of a difference. But either of these might be reasonable forecasts to use for what the unemployment rate looks like. Now, one thing you should bear in mind, this is what I would call a numbers-driven process. What's producing these forecasts is just what the numbers have looked like in the past. There's no intelligence being applied to this. There's an example in the book of what I call a hybrid model, which is generally what you want to do, which is not just be driven by the past. The past here is a fairly regular pattern, so at least the seasonal fluctuation, I think you'd want to use as a basis. It's a pretty well-established seasonal pattern that's gone on for, in this case, almost 30 years. So I'd want to keep that. But if you're trying to forecast what unemployment will look like in the next year, you probably want to take into account how likely is it that we will go into a recession, what does the growth rate of the economy look like. There's lots of expert opinion forecasts out there. I'd probably want to use this as a baseline, what the numbers are telling me, with some judgment then being imposed on top of that. So if I really want to forecast unemployment for, well, in the next 3 months, I might want to stick with this. This might be good enough. But if I want to do it for the next year, I probably want to add in some additional things that might deviate from just what the numbers are basically telling me. So the numbers-driven process is of value, but once you get beyond a very short time period, you want to take into account what might change this pattern. And there's a good example in the book where things like tariff wars would be expected to change a past pattern, and you can actually model that, and you should model that. But when there is a strong historical pattern, I wouldn't want to ignore it. I'd want to use it to the best of my ability. And that's the number-driven process here of these two models here, the autoregressive moving average or the moving average with seasonal adjustment, both give us a fairly good basis or baseline to then develop a more sophisticated prediction from. For a short-term prediction, these would not be bad to use. Now, let's say you were interested in predicting not just Alaska as a whole, but you wanted multiple regions. So I picked a number of regions here from Aleutians, Mat-Su, Anchorage, Bethel, Fairbanks, Kodiak, and North Slope. And if you highlight all of them, you can save yourself a lot of time potentially by going under time series to what's known as a batch fit. The batch fit will not only just do them all at the same time, it will also take into account correlations between them. And you might expect that there would be some correlation of unemployment in different parts of Alaska. So if you go to batch fit, you get a similar kind of dialogue. But you'll notice that there is an auto detect button, and if you click that, it will use auto detect when it goes through all of those fits. Before I fit it, let me just put here on the report, you have some options to whether or not to include correlations, and one of the main reasons to do batch fit would be to include it. And do you want to have detailed reports? And I think they'd be useful to look at here. So we'll have a separate worksheet for each of these regions. And the series, just which models it will use by default, it tries all that it can. Go fit. It creates a new workbook, and there'll be a sheet for each of these regions. It's going to take it a minute. So before you use the summary, let's just look at one of these. If you look at the Aleutian East, it's showing the best fitting one was a moving average 2, but it's showing each of the methods that it used here. There's the best one out here in column M. It tells you what it did, basically. It has transformed the data. It's used a logarithmic transformation, which is the most common one. It's found that it can fit the data better if it transforms it first. So what it's doing, and it's using a first order differencing. So basically it's looking at the change month to month of the logarithm of the unemployment rate. So you could do all this by hand, but it's a lot of work. And basically it has said it can fit this data better if it takes a logarithmic transformation of the differences between each month unemployment rate, uses additive seasonality, and notice it has used a 6-month seasonal pattern for the Aleutians. If you look at the Mat-Su one, it has not transformed the data. It is using first order differencing, and it's got a 12-month seasonal period. Anchorage is a 12-month seasonal period. Bethel was 12 months. Fairbanks was 12. So for some reason, the seasonal pattern, well, actually Kodiak and the Aleutians both show a 6-month seasonal pattern, which might make some sense and probably worth thinking about, but you might also want to override and have forced it to use a 12-month seasonal period. But there's good information maybe in what seasonal pattern is picked up. 6 months might make some sense here, and 2 of these regions, both similar locations, sort of have picked up a 6-month period instead of 12 months. When you look at the summary, it's taken all of the best fitting ones, it's put them here, it's actually inserted the function here. So if you were to randomize this, as you press F9, it's actually running the simulation. So if you want to simulate, it's, I think by default, put in 30 months of forecast. You don't have to set up these cells, they're already set up for you, and it will run a forecast for up to 30 months for each of these regions, incorporating the correlation matrix that's put below. It won't handle fancy copulas, it's just using a Gaussian copula, so it's the simplest one, but it gives you a correlation matrix. Notice this right here, Anchorage and Mat-Su are perfectly correlated. Not surprising, because in fact it's pretty much the same employment market. If you look at the other one, if you look at let's say Anchorage compared to Fairbanks, there seems to be some modest positive correlation. There's a somewhat noticeable negative correlation with Kodiak, but actually it's not very strong. -0.27 is not a very strong correlation. Very low correlation with the other regions. In fact, if you look at the Aleutians, there's very low correlation with any of the regions. There's a very small, even with Kodiak, it's not very substantial. So in fact, most of these correlations are really quite small. Alaska's a big state and the employment markets are not closely connected, with the exception of Anchorage and Mat-Su, which are perfectly correlated and somewhat noticeable with Fairbanks. So that correlation matrix is included in these models. You'll notice that if you look at all of the things that went into this moving average 2, it includes the CORMAT, the risk CORMAT, which is a correlation matrix. It has included that. This is position 1. If you look at the second one, it has position 2 in that correlation matrix. So all of that's built in, automatically ready to simulate. So batch fit can be extremely useful and quick, but I think it's important, as easy as it is, that you do sort of keep your eyes open and your head thinking about what it's done, because the automatic part of it can be deceptive. You do want to, when you go to batch fit, you do want to pay attention to, if you're doing auto detect, I think you should look for all those sheets, separate sheets, so that you can see what it actually did in each of these markets. Or alternatively, you could say, well, I think we want to use a logarithmic transformation. We'll use first order differencing, and we will deseasonalize with 12 periods. Instead of auto detect, you could choose to do all of those. Click fit. You'll get the same kind of output, except that it's going to always do the same thing that we just asked it to do. Now, if you look at like the elutions, and seems to have done something pretty strange here. I don't really think auto detect worked better, because it's something, the mean prediction here somehow got off the charts. So using the 12-month period and the logarithmic transformation did not do well on the elutions, I would say. So this one example would lead me to believe auto detect did a better job than my forcing it to do this. I would just caution you, that's not always the case. You should be a little bit careful, make sure that what you're getting does look like it's mimicking the data pretty well. It is a data-driven process, so it's not, I think this is the right forecast of unemployment? Does it look like it's imitating the past patterns well? That's the way to judge whether the model that it's come up with or that you forced it to use is a reasonable model. All right, I'm going to show one more example and leave it for the book to handle further. Okay, this data set is flu cases, weekly data for the last 10 years. This is from New York State. You can download a lot of flu data. Some of it's painstaking because it's in different reports for each week, and the CDC does not make this easy. Although if you're familiar with the R programming language, somebody has built a nice R program to go out and collect all of the weekly data from the CDC if you want. I just took what was easiest for me to find, which New York State has 10 years of weekly data reported. These are the total flu cases. They do it by county. I actually just aggregated all the counties, so it's the total for reported flu cases for the state. I would start in the same place, which is look at the data. And just insert a line chart. So, level, you can see that there's a lot of low weeks. We have these seasonal, 10 years, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like the second year there was a very mild season. You can hardly see the peak. The other ones, it does seem like there's a regular pattern that is occurring in that there's a flu season, which is much higher than the other weeks. It was a really bad year right there. Generally, in most time series, you're going to find that it's easier to model the differences from one week to the next, the changes. But one of the nice things about the way the at-risk does this is it will automatically handle that for you. You don't need to decide to create a column of the changes like we've done in other data sets. It will handle looking at the differences automatically for you. So if we go back and highlight these flu cases and go to at-risk, fit a time series, mean and variance appear to be non-stationary. Generally, that means that if there's trend and seasonality, they're not being picked up automatically. If you were to go directly to fit here, it gives you a warning that those were non-stationary. And look at the black line, the forecast. It's basically giving you a flat forecast and equal to pretty much the average of what all the weekly data look like, because it's thinking of, by not making any transformations or any manual overrides or any auto detect, you're basically telling the computer, look at all of this as if it's random variation. And if it's all random, what it's going to do is pretty much predict that each month will be, each week is in the future is going to look the same, and they're all going to be about the average of what historically has transpired. Not a very good model. Now, if you go back, when you click auto detect, it's managed to get rid of, or to have a stationary, which means it's able to model the mean level and the variability of it. And when it's modeled that, what remains is random variation. So it's been able to get rid of both by using the square root as a transformation. It only has 2 transformations built in. You could do by formula fancier things, but many time series you'll find either logarithmic or square root is all the transformation it needs in order to more accurately model the trend and seasonality. So it's done a square root transformation. It's used for sort of differencing, so it's actually transforming. It's looking at the square root of the week-to-week variation with additive seasonality. And notice it's picked up period 32, and I had to look back at the data to actually see that, in fact, these are CDC weeks. There's 20 weeks of the year that are not part of the flu season, according to the CDC. So the CDC reports weekly data for weeks 1 through 20 and 40 through 52. First 20 weeks of the year and the last 12 weeks of the year. Flu season starts October 1st, and it ends whatever number of weeks it is to get to week 20 of the year. And that's the end of flu season. So there are 20 missing weeks in each year. And it has picked up that there's 32 periods of seasonality, which is correct because there's only 32 weeks that comprise each of the flu seasons. So it's done a good job picking that up. When you do fit, it's important visually to look at the fit. Notice the mean forecast here. So we're starting at, let me pull that over for a minute. Oh, I can't do that. Well, we'll see where I forget what the last week is on this, but where we're starting is sort of early in flu season. So you see the flu cases are the black line increasing. And right now it's forecasting kind of a similar peak to what, to one of the lighter flu seasons. Now, of course, there are there are guides to whether they forecast a bad flu season or not. It has to do with what's going on in the southern hemisphere, which has a flu season kind of, theirs ends when ours begins. There's expert, predictions, so you would probably want to modify, but I think there's been a regular enough pattern that this would be a baseline to sort of start from making your forecast from. And there's a famous example of Google flu trends where Google was trying to use Google searches to try to predict the flu season, and their model actually went terribly wrong. So it's a famous case. You can Google it, you'll find that Google has stopped trying to forecast flu trends because their model didn't work. But this is what's known as Brownian motion. A Brownian motion model is a random walk. It basically ignores the history. It just says, where are we now? And from wherever we are now, it will do a random walk. But it is using the historical pattern in the sense that it's the extent of the randomness is based on the removing the trend and seasonality that was exhibited in the past. The seasonal pattern, there's no trend. The seasonal pattern is what's been removed. Once you remove the seasonal pattern, the random variability is being estimated as a random walk. A moving average was the second best fitting model. And if you compare these, there's a little more uncertainty with the Brownian motion, but again, it's not necessarily a bad thing because when you look at this history, I don't know that I want to be terribly accurate. If I got a terribly accurate forecast for the next one, I'd be suspicious of it because there's been so much variability from one flu season to the next. So having more variability probably means it's a better forecast to use. The autoregressive one, these are all fairly similar in terms of, if you look at the black line in the middle, the mean forecast looks somewhat comparable. In some cases, a little bit smaller than in others, but not terribly different. Go back to that Brownian motion one and you animate it, watch the red line. These are the possible flu seasons, and noticeably they seem to show some possibility it will look like some of these bigger ones from the past. It could be as bad as 2 years ago. Most of them are much smaller, modest flu seasons, but occasionally a noticeable number of times you get pretty dramatically high forecasts. That's probably based on just the past history, the best you can do. When you look at this past history, we should expect some possibility it will look like this really high year, but not as frequently as a much more modest one. That's what I mean by a numbers-driven process. It's being driven totally by the history that you gave it to look at. And so it's called a forecast, but when we hear the word forecast, we often think about a fairly intelligent process where we are applying all kinds of knowledge to it, and we would call that a forecast. But the short-term forecasting methods that are being built in here are totally numbers-driven. They're just imitating what the data is suggesting to you. They're not applying any kind of judgment or causation to what might be different that's changing things. So I think that's not a bad model to use. Generally going with the best fitting one is what you want to do, unless visually it just looks bad. If it didn't seem to be showing the black line that it was expected to increase, I probably wouldn't use a forecast because we're early in the flu season at the end here. Where are we? At the very end, we've just started flu season. Week 40 is when it begins. So this was the first 3 weeks of October. We should be predicting that it's going to ramp up from there on out. Just remember, this is New York, so their flu season starts, it starts fairly low in October before it gets to much higher numbers later in the season. So we should be expecting it to ramp up at that point in time. And if we saw the best fitting method for whatever reason was not expecting it to ramp up, I wouldn't use that forecast because it's clearly not imitating the past pattern. It's not to say that we might have a flu season where it doesn't ramp up in October, but given the past patterns, there would be no reason to get a forecast out of this past data that did not ramp up from this point in time on. As to how high it will be, there's some possibility it will be as high as this season here. More likely it will be a more modest season than that, but that's what that method seemed to pick up. So your two basic things are to use the fit or the batch fit. Either one of them, though, auto detect, I would try, but I would also then look at the details of what it's detected and say, does this look reasonable? You can always override it and manually adjust it, and you can go, when you go to fit here, you click auto detect. If you want to override it, don't auto detect, but click this off. Manually decide that you want to use a logarithmic transformation with first order differencing and deseasonalize it. You could try that instead of the square root. Try the fit. Look at what it's giving you. The logarithmic transformation here is actually the reason why you see the blue line, the history is sort of compressed, is with a logarithmic transformation. It kind of squashes the data down. It eliminates the extreme values because in logarithmic transformation, extreme values become a lot smaller. But it also looks like it's giving me some fairly extreme forecasts. Yes, it's hard to see where the red lines are. You can see them popping around, but they're a logarithmic transformation. It's a little change is actually a fairly large change in the data untransformed. I'm not sure what, I guess this is the mean line. It seems extremely high because a logarithmic transformation squashes the really large forecasts, but the large ones will produce very high numbers. The mean here is ridiculously high. So you can see, and occasionally it's those red ones that shoot up that is making the mean forecast that high. So this does not look better than what the computer came up with. I go back, and if I were going to manually do this, at least change it to the square root. And then you're getting essentially what AutoDetect came up with, the Brownian motion, and seems like a much more reasonable forecast to use. So this is what I mean by use your eyes and your head, and basically don't just press AutoDetect and ignore it. Look at what it's giving you and assure yourself. Most of the time I found AutoDetect works pretty well. Occasionally it misses, so you're going to have to catch that, as AutoDetect just does what it does, and if it's doing something silly, there's no way it knows, so you're going to have to tell it that. But fairly easy to fit time series. These are not all the models that exist. The book discusses sort of what the logic behind these models are, but this is a pretty good array of time series models. That there are fancier ones out there, but these actually cover, a vast majority of the kind of data that you're likely to want to look at when you do time series modeling. So with that, I will stop this recording.